This is our machine learning project titled Artylyze. We aim to analyze historical paintings using machine learning techniques. Since the advent of digitalization, millions of artworks have been digitized, opening up the world of art to countless new people. However, navigating this space for a layman is difficult due to the lack of metadata and contextual information needed to describe and understand the artwork. In this research project, we use both supervised and unsupervised models to generate metadata given an image of an artwork. Specifically, we will predict the genre and style of the artworks. Throughout history, it has been observed that artistic collaborations fuel creativity and give rise to art movements. Our study aims to find correlations between different artistic styles spanning geographies and periods, which would help track the journey of art and how it evolved. Soft clustering approaches can help deduce the influence of different factors like genre, time period, and geography on a particular work of art. Studying the similarity and influence across time and geography between different art styles is a relevant research area. Furthermore, our tool also aims to automate the tedious task of art classification in art galleries and museums. Here, we discuss some previous literature and work that has been done to tackle this problem. Previous work has used methods like CNNs and random forests to predict style, genre, artists and time period given the image of an artwork. We refer to these works when doing our comparative study on various techniques employed. Before we begin our discussion, let's talk about data. We collected a dataset of 12,000 images, which is a subset of multitask painting 100K dataset. The dataset has 100,000 images from 1508 different artists but only contains artist name, style and genre. We used the 50 most famous artists from Best Artworks of All Time dataset to filter out artworks and combined the two datasets to get a subset with artist name, genre, style, nationality and year of work. The final filtered subset has a total of 12,619 images split into train and test set of 8,837 and 3,782 images respectively. Now, let's talk about dataset pre-processing, which is an important step in improving accuracy and reliability of the models. In our case, we noticed that the dataset exhibits a class imbalance issue. A classification dataset with skewed class proportions is called imbalanced. This can cause a classifier to be overwhelmed by the majority classes and ignore the smaller ones. In order to solve this, for genre classification, we select the top 12 genres and perform undersampling to get a class-balanced dataset. Before using any unsupervised classification method, we need to perform feature extraction, which is basically obtaining a rich, informative and compact representation of the input. For our unsupervised classification, we use the following methods for feature extraction: PCA, kernel PCA, VGG16 and MobileNet. In each case, we get a linear vector of reduced dimension. For the PCA techniques, we retain 95% variance. Feature extraction is a very important step since that will help our model understand which features to focus on to define similarity between images and perform meaningful clustering. Talk about data processing for supervised classification. We want our model to generalize well and focus on important underlying features for genre and style prediction. Thus, we perform a few simple data augmentation practices like flipping and rotation along the vertical axis. We also standardize pixel values. In the figure, you can see various transforms applied on the leftmost image. Data augmentation helps reduce overfitting and improves generalization. We will now discuss the methods we used to solve the problem. We employ both supervised and unsupervised methods. For supervised classification, we use a CNN architecture. For unsupervised analysis of similarity and artistic trends, we leverage clustering algorithms K-means, which is a hard clustering method, and Gaussian mixture models, which is a soft clustering method. Starting with supervised classification using CNNs. We experimented with various CNN backbones and learning rates, with a fixed classification layer architecture. Here you can see the various parameter settings for our model. For the classification layer, we used two linear layers with ReLU activation after applying average pooling, combined with dropout, as shown in the figure. We also scale the image from a 180 x 180 to 100 x 100 dimension and set batch size to 32. For unsupervised clustering using k-means, we used the elbow method to obtain the optimal number of clusters, which came out OTB 25. Here are a few examples of the clusters formed from different feature extraction techniques, depicting how the clustering is able to group similar pictures together. The cluster on the left puts together all face portraits, while the one on the right puts together boxy colored designs. For unsupervised clustering, we also used Gaussian mixture models which perform soft clustering. We can hence use GMMs to understand the influence of different genres and styles on a particular painting. The responsibilities obtained for different clusters, given painting, can be used a measure of the influence a particular style or genre has on the painting. For example, this particular painting, the highest responsibility value is 0.99 corresponding to cluster 8, and it can be observed that the styles are very similar. The painting also has non-zero responsibilities for clusters 24 and 6, and the influence can be observed in the style. Finally, let's discuss the results. For the classification task, we use a combination of F1 score, ROC-AUC curve, top K accuracy to evaluate model performance and compare different models. Since we do not have access to ground truth cluster labels, we will be using internal measures such as silhouette coefficient, Davies-Bouldin index to evaluate our clustering algorithms. See the metrics for different backbone architectures and learning rates. We first experimented with a small 3-layer CNN, which was extremely noisy as its capacity of learning is lower. Then we tried popular backbones like MobileNet and DenseNet, which gave better results. MobileNet is a strong yet compact model, and DenseNet utilizes dense connections between layers, which helps overcome the vanishing gradient problem. We show metrics obtained with both a frozen backbone and fine-tuning. The DenseNet backbone with fine-tuning obtains the highest accuracy of 0.64. We used the same model for our style classification task and obtain an accuracy of 0.51. Here we see the metrics for different clustering techniques while using different feature extraction methods. Different clustering techniques use different distance functions when clustering points, and the separation of classes is highly dependent on it. Though the metrics are bad, the clustering does show good results qualitatively. Different clusters are able to group similar images together to a good extent, as shown earlier. In conclusion, we saw that CNNs are able to differentiate between complex and overlapping genres. Then we noticed that for unsupervised classification, feature extraction and distance metrics matter more than the clustering technique. We can clearly observe through the distribution of our clusters that artworks have a lot of influences guiding them. Cluster distributions span across nationalities, time periods, and artists. Through this work, we have been able to shed some light on the high correlation between artworks of different genres and styles, bringing out the fact they took inspiration from each other.